So yeah, welcome back everyone. Today I want to do a little bit of a tour, or detour is maybe the wrong word, but something that I could have included much earlier. So I want to talk about the ring spectrum. And give you a bunch of examples and sort of connect this abstract theory somewhere with something a little more classical. So my justification for putting it here is the following. So we have so far looked at these big function formalisms defined in some category of schemes and have, studied this to some extent. So how can you get new six function formalisms out of this? Well, you don't have that much tools in your hands. Basically, you can append a symmetric monodic functor on here or there. And so what's going to be interesting at the point, so given an algebra object in D of our ground scheme, so this could be the ground field, if this C is schemes over a field and so on. So given such a primitive algebra object, we can consider the following. You can send X to what? Well, you have this D of X, this old six function formalism, and you tensor over D of the base scheme with A modules inside there. So that's something you can certainly do. And it's not hard to see that this is also a six function formalism because basically, well, whatever you do here on this level, f of a star and f overstreet, they will be linear over D of star, and so you get a new six function formalism. Yeah? So this is a new six function formalism, and my goal today is to somehow shed some light on this. So what interesting A's can we put there, and what does this bias say? And as you will see, this has now basically the study is, or the question is, or the goal, therefore, is to find interesting examples of some such A, and especially for us, you see, of course, this makes sense for any six function formalism, but given that our home base is this SH, especially you want to find A which are computed algebra object in SH over some scheme, and that scheme is usually just space. Yeah, so and this is so such guys are called Motivic ring spectra. Yeah? So I mean Motivic because SH and ring because or E infinity ring spectra implicitly rather. Yeah. So that's our goal today. So I want to present a few examples of such A's and tell you a little bit about them. The first thing is actually very easy, I mean, at least from the outset. So let me call this maybe coefficient ring spectra. So this is what's going on here. This is something very, very innocuous. So we have this, so I remind you this D of star, maybe I should have said, but D of star is, well, of course it's stable, yeah. And because it's this star is here the monodal unit in here, this is also a symmetric monodal unit. Right? So and as such, it receives the fundamental spectra, which sends the sphere spectrum to the monodal unit there. So 1 maps to 1. So okay. There is this unique such totally preserving symmetric monodal functor. And in particular, we can say that given a commutative algebra object in spectrum, we will get some A, which I still call in this probability on that point, quote-unquote point. Yeah? Okay, so that's obvious. In particular, we want to apply this to A being isomorphic ring spectra. Yeah, so I remind you that if you have a normal good old ring, then this becomes a spectrum by means of this so-called isomorphic ring factor. And so in particular, V1 values to Q and things like C1. That's actually the only real cases we care about, but of course this works general. And so, okay, this is now something we can do. And so remark. So let's unwind this thing here a little bit. So yeah. So what is I need to produce one notation. So I want to call this d a of x, or a of x. And in the context of this section here, I want to call this a lambda. I don't know, people like use lambda for such a coefficient ring. So what is this d lambda of x? So so this is just going to be d of x, and I mean here I have tensor over d of point with modulus in there. But since that a came about from spectra, this is also the same as if I tensor with over spectra with modulus over this lambda inside spectra, right? So that's what I get back here. So I don't need that. That's slightly more fancy base ring product. So spectrum. And a quick observation is the following. So if I mean, this looks like a little bit of a beast, but actually it's not. It's something very, very tangible. Namely, if Fi in d of x happen to be compact generators, I mean, I'm not. I mean, this whole kind of makes sense in general, but if they happen to be compactly generated, then we can say the following. So then I can take Fi, then I already like this. So Fi box lambda, so this is Fi in here and the lambda in there. These will be generators, and in fact, compact generators of this d lambda. Yeah, so in other words, basically you have the old generators as before, except that you keep in mind that you have the lambda somewhere. And so the generators are the same up to the bijection. And what are the mappings? So map in this d lambda of x from Fi box lambda to, let's say, j box lambda. Well, if you unwind the thing, and especially using the compactness here, then you get the mapping space in this d of x in the original category of Fi to j, and then tensor, if you wish, the mapping space from lambda to itself in the lambda module. So that's certainly just the lambda. Yeah, so in other words, you really, under this compactness assumption, you just tensor whatever cohomology you had basically with lambda. Okay, so for example, once again, if lambda is especially when it's Q, then you really just kill all the torquing from all these homotopy groups. So yeah, that's what you should have in mind. In some sense, this thing here is of course now much more general, so we will not just tensor the mapping space with a particular ring spectrum, but rather, well, it will be more powerful somehow. But anyway, that's something. And so I mean, this is all very formal and in some sense cheap. And what is not cheap is the following theorem, which is called the so-called rigidity theorem. So there is some assumption. So I will leave a little bit of space to take notes, and the theorem is now the following. And I will put the assumption in a moment, but just wanted to write down the statement. So that x be a scheme, and some n, some non-zero integer should be invertible in OX x. Yeah, so x might be over a field, and then this n might be prime to the characteristic. That's the usual setup. And then lambda is this algebraic spectrum of Z mod n.
Sorry,
Yeah.
which tensor problem is that?
This one here?
Yeah.
Yeah, that's the tensor product in spectra.
So the mapping space is.
So this is the mapping spectrum,
Okay.
strictly speaking. I think I said mapping spacing, but I want to say mapping spectrum. So that's the spectrum whose
Yes.
all of its homotopy groups are the good old Hom in the homotopy category. And so it's seen all the homes. Yeah.
So also the other one, not D lambda.
Yeah, right. So this map is it's the mapping spectrum, all of it. Which makes sense because we are looking at the mapping groups. Okay. Good. So let me go back here. So that's the situation. We have a scheme, and there is going to be some some sort of finiteness assumption. So we assume, and I will say what this is in a moment, x sigma lambda is, well, let me say admissible. I will say what this is in 1 second. So it's a certain finiteness condition. Then there is an equivalence. Maybe I should say this is called rigidity. The rigidity theorem for étale motives. So we have the derived category of étale sheaves with lambda coefficient. So this is really the good old classical SGA type category. You have 4 étale sheaves, you take the derived category. And then there is a function from here to the étale category SH étale, so sometimes also called étale motives, with coefficient in this ring lambda now over X. And functor, what does it do? So you have to decide where your representatives go. So if you have F, which is some étale map, then you have the representative pre-sheaf, F lower sharp of lambda, and this is mapped to F lower sharp of lambda, where in both cases this F lower sharp is the left adjoint of F upper star. Yeah, so this is kind of the obvious functor that you have. This functor always exists, but under these assumptions, namely, this exists without the lambda, and the lambda is not crucial to define the functor, but if you do this, then the statement is this is an equivalence. This is a striking thing because you see, if you look at the definition here, this was defined in terms of smooth schemes over the space X, whereas this one you only take into account étale things. Yeah? So this is a much more computable category than this one, but it turns out this is equivalent. And so now, what is this condition here? So this is the mild technical condition. So let's say definition X comma lambda. So this depends on the X and on the lambda. So it's kind of they play together is admissible for the purposes of this theorem here. If the following is true, if for all points X in X and all finite index subgroups of the residue of the Galois groups. The Galois groups of the residue fields, we have that H by G comma blank is 0 for large enough for a certain integer which depends on which might be on the point X. Yeah, so in other words, you want that for all these points, and to be precise, all these finite subgroups, they have to have a bounded homological dimension, where the bound might depend on the point. Okay, so that's the condition, and so it looks a little bit artificial, maybe. So maybe let me just say example. This is true when X is of finite type over, for example, a finite field, or an unbrightly closed field, and in other situations, it's not always true. So not true for X being spec R, the real numbers, and lambda being Z mod T. Yeah, if you have that, then you realize, okay, the Galois homological dimension of its Galois, which is also Z mod 2, is infinite. So there's some. It's not always satisfied, but sort of many times it is. And under this my assumption here, once again, this category of étale torsion motives, as you might call it, collapses to something much more classical. Okay. So that's the statement. And this statement, since I'm, maybe I'll just say orally. Of course, this is due to many people. It has been kind of extended several times. The first person to name here is Suslin, who came up with the so-called Suslin rigidity, which is the statement that algebraic K-theory of algebraically closed fields is insensitive to what the field is when you work with formal coefficients. And so I will not try to give a proof of this. I will just make a few remarks about that statement. So I'm trying to convince you that I'm trying to help you remember, let's say, that you have to have at least these formulas. So why is that? So if you believe that statement, some alien comes to you and gives you this statement, and then you are trying to probe it and trying to see what does it value, then you observe two things. Namely, one is that the left-hand side is insensitive to, let's say, if you have one separably closed field and you have another one which is also separably closed, then we know that étale sheaves over such a thing are basically just disjoint unions or copies of these fields. Yeah? So the left-hand side collapses very much. The left-hand side is then just equal to the derived degree of lambda modules for either of those, and independently of how the field is. And so if you believe in the statement, that tells you, so the theorem tells you that SH of K with lambda coefficients is again insensitive to such field extents. Yeah? So that's what the theorem tells you. And so why is that? How does this kind of feel? Or let's poke or probe this result in one small way. So if I'm saying this is an equivalence, that in particular tells you it's fully faithful. Yeah? So if you have this field extension, you can do a pullback. So in particular, it's fully faithful. And let's shed a little bit of light on this by looking at the Hom set in this SH from from 1 to 1, twist 1, shift 1. Okay. So what is that? So this 1, twist 1, shift 1 is just the sheaf GM. And so you're going to get K star. Okay. So in the Hom set, and now here it's the Hom set. Yeah. So this would be the pi 1 of the Motivic spectra we talked about earlier. Or pi minus 1 rather, pi minus 1. But anyway, so we get these units here. And so if you forget about these coefficient lambda here, then you would talk about K star magnitude K prime star. Of course, they are clearly not isomorphic, but now this tensor with lambda here rectifies this. If you do K star tensor over Z with lambda, so lambda is over Z mod n. So of course the tensor part is derived. So this is basically a two-term complex K star magnitude K star, and here you have the nth power map. And this is in fact quasi-isomorphic if you replace K by some other value. Yeah, so even though this K prime might be, think of K prime would be K adjoint T bar, right? So this would be a much larger field, but if you look at this here, this is in fact quasi-isomorphic to Z mod n, because the Kummer sequence tells you, it's surjective, and the kernel is the nth roots of unity, right? And so they don't in fact depend on the field. Yeah, so this is true thanks to this thing. Yeah, so we see this this tells you have to do something. You cannot work integrally because of course these units they will mess up. They will clearly not be insensitive to the field. That's one thing. And the other thing I want to comment on is sort of probe the result from the other side. So if some alien again gives you the theorem, what does it tell you about the left-hand side, given what you know about the right-hand side? So the right-hand side is by definition a one invariant, which means that SH of X, SH total of X, is fully faithfully sitting inside SH total of X times A1, right? And now let's take a lambda here. And so if you again believe in the statement, then you have P étale of X times A1 lambda, and here again, P étale X lambda. So this would tell you, the theorem tells you this is fully faithful. Okay, which means in particular that sheaf cohomology is a one invariant, étale sheaf cohomology. Yeah? So this tells you, this being fully faithful tells you Hm of X lambda is isomorphic to Hm of X times A1. And that is true. I mean, it's a fact we know about the typology, which actually goes into proving this. And so you see, you have to have this homogeneous invariance for a typology, which again uses that n is very distant, n is invertible. Okay, so you couldn't work over FT with zero coefficients. Yeah, so this is known and use this n is invertible. Okay, so over FP, if you work with FP coefficients, it's not going to be invariant. Yeah, so you see, and I mean, once again, this fact is in fact used into proving in proof of this. Yeah, so the proof uses a bunch of inputs, but among other things, all these properties you basically know about time homology. So it's not kind of a miracle bullet, silver bullet somehow that solves all your problems, but rather all the work from XTA, etc., has going into this. Okay, so anyway, this is an example that is very interesting. So it's telling us that the time models with torque coefficients, they reduce something drastically similar. It's unfortunate or fortunate, depending on your point of view, that no such thing is true for rational coefficients. So there's no similar simplification like that. So that's really only for total coefficients. Yeah. So that's one example of a ring object in SH. So now I want to talk about ring spectra representing wave homology theories. And so I will do this example of dynamic homology, just because dynamic homology is maybe the most down-to-earth homology in some sense to handle. So what is the paradigm here? So paradigm is the following. So we have this category D star, which will be SH or stack, ground ring, ground field, whatever, in a moment. And so we are trying to find another object here. And so what if we had a functor from here to some other presentable presentably symmetric monoidal category? What if we have a functor that is again, symmetric monoidal and in parallel? If we have such a thing, this will have a right adjoint. Okay. And this right adjoint will be less symmetric monoidal. In particular, given if we have an algebra object in E, we can send this to something which is going to be an algebra object in this D of star, right? Because that's like symmetric monoidal. And so very often one applies this to A being actually the symmetric monoidal unit in some nice category. So in particular, if you manage to find a functor symmetric monoidal and it's called preserving from here to somewhere, then going back from monoidal unit will give you an interesting object that we can look at. Okay? So that's a very, it's again not this technique from that point of view, but it turned out to be very powerful. And I want to illustrate this now with D again in SH, and this category E will be the category of complex character spaces, and this functor F will be the so-called boundary prediction. So here's the statement. So let K be a field of characters 0, and then there is a symmetric monoidal and causally preserving functor from, so I call it goal, room for realization, from SH stack K to mod K. So the right category of character spaces. And the SH here for the purpose of this, I want to focus on SH in this neighborhood. I mean, the other one would work as well, but that's just that. So what is that functor doing such that if I apply this to the motive of some x, which is smooth and affine over this ground field, then I'm going to get the Delan complex of that smooth affine scheme, but dualized. In some sense, this functional rho Delan is kind of like a Delan homology, if you wish. Yeah, so because of that dual. Okay, that's that. Yeah? So we have a symmetrical non-functor that spits out somehow this Delan complex. And we will in a moment then apply this paradigm to that functor and see what modules over that Fi there will be. But first I want to say a few words about this here. So, and again, I hope it becomes clear that this is not really very sort of, I mean, you can play a similar game with many other cohomology theories, such as, I don't know, yeah, the lean cohomology and so on. And so this can really be squeezed more. So this is meant to be an example of a technique that applies for other things as well. But anyway, let's look here. Yeah. What do we have to do? So we want to use goal or idea is we have this universal property, right? So we have smooth schemes over K. At the end, we have SH over K, and we would like to have a function from here to mod K. So what do we have to do in order to get such a function? We do step by step, right? So we have pre-sheaves of smooth schemes over K, which is the embedding, and then we have this pedigree of Motivic spaces, and then we have this pedigree of pointed Motivic spaces, and then we have this SH. And so basically what we are trying to do is we are trying to say getting a function out of here to some presentable category is basically you have to know what to do on schemes, and then you have to have a bunch of conditions. And so let's first not yet worry too much about the beginning, but let's sort of look at these conditions. So first claim is this functor, and I will now use so x will be spec A, so we can assume everything's affine here for the purpose of this argument. So I claim this functor A maps to omega A over K has satisfies. I mean, this image, this in particular, even BT that is set. Yeah, so i.e., if A to B is BT et al plus faithfully flat, then omega A, so maybe I'll drop the K, yeah? Omega A is isomorphic to the limit of omega B, mapping to omega B and to BA, and so on. Yeah? So that's the statement. So in the notes I've given an argument. So the argument, of course, does use the BT et al and faithfully flat. Maybe I'll refer to the notes for that. Yeah, so this is sort of this omega behaves like sheaf for the nuclear topology. Secondly, this is homotopy invariant. This omega A adjoint T is quasi-isomorphic to omega A. Again, okay. So here we use that the characteristic is 0. Yeah. So if you think about it, you realize this works. Actually, it's an interesting little observation. If K is of positive characteristic, then this is not true anymore. And if you render this Delan complex homotopy invariant, it becomes 0 actually. So there's a nice insight due to L1. I'm not sure if it's just a curious coincidence or anything deeper, but in any case, this is necessary here. And then so this, finally, the following thing is true. The co-fiber of this omega over A1, K over K, to omega of GN, K over K. So let's parse what that is. So this guy here, by what I just said, is just quasi-isomorphic to K in degree 0. This one here, what are its cohomologies? Well, again, there's cohomology degree 0, which is also K. And then there is in degree 1, there is K times dt over t. That's the h1 is also one dimensional. Okay. And so the cofiber of this, they will kill these two k's, and this will remain. So this is as Motivic 2k in degree 1, which is in particular, which is invertible, crucially invertible in this mod cube. Yeah, so that refers to this thing. Okay, so now we would like to say, hey, cool, we have a functor from SH2 over here. The only problem is that functor is actually not covariant. So if you think about it in terms of smooth schemes, x mapping to omega s is actually contravariant in the scheme. So what we have is the functor from S and off all the way over here that otherwise looks like it wants to fit into your bill, but it doesn't quite because of this annoyance with the wrong variance of the functor. And so what we can do is we can realize, get rid of that problem. So it's here where something non-trivial happens. So fact for x in smooth schemes over k, this complex omega x over k is a perfect complex. Which means two things. One thing is the cohomology is limited finally in degrees only. Okay, that's not hard to see, but what is harder to see is that all these cohomologies are in their own right one by one finite dimensional. Yeah, that's what we see perfect complex. And that is a statement which follows, which uses the resolution of singularities. And so in the notes I've given a reference. It is also possible to, this reference in the notes refers to doing this computation just for omega. One can do the same computation in some sense, just staying within SH, which I think we'll also talk about later. But for the moment, maybe let's accept this as an input that these complexes are perfect. And so what does it buy us? Well, now we can do what we do here. So we can consider the function from smooth schemes to where? Well, I want to say, so x goes to omega x again. So this is now, so initially it's a contravariant functor, so it lands in mod k off. But what I said here is it lands actually in perfect complexes. But of course it's still contravariant. But now I can append to this functor here the equivalence which is given by the dual, of course, dualized objects. I can do that. So I land in perf k. And then again I can go to, and now I can let this, forget about it being perfect and just go to mod k. Yeah? So this composite is basically the old one, except that I do the dualization, like I said here. Okay. Okay, and so now what's going on? Now all these conditions. So here I said it even satisfies pro-atomism, but we only care about this Motivic excision. So this Motivic excision held before we dualize, and then we dualize. It's still going to be fine. This one as well. This one as well. Yeah. So you see this process of dualization doesn't kill any of these properties, and so this functor here does factor. Maybe I'll put it in here. Does factor over this rule enough. Okay. So good. So in other words, up to this little twist here with taking the dual, the existence of this functor ordered on is basically just a nice way of packaging all these properties of the complex into one mathematical sort of entity. Yeah. And this is also what applies to other cohomology theories. Yeah? So if you have other cohomologies having similar properties, then you again get such realization functions. Okay, so that is this functor, and now let's get back to this paradigm here. What are these modules? that we coop up there using that. So yeah, maybe let's say definition. So this H divan, I define it to be rho divan and then the right adjoint. The rho divan was here this function. It has a right adjoint. It sounds very more crazy to look at this, but let's still do it, and let's apply it to the model unit, which is K here. So this, whatever it is, it's at the very least include a value object in SH. Okay, right? Because once again, this right adjoint is less semantic monologue. Okay, so this is some beast. Of course, the divan, it's sensible to put divan there, but you might ask, what is it really, right? And so here's the answer to that. So corollary of the thing there. So let's do this funder de divan, or maybe, yeah. So this is modules over this H divan SH. So this is a funder from this category of correspondences, let's say, of schemes of finite type over K. To case to get our characters to 0, to PRL stable. Okay, so this is what it is. So once again, it sends X to modules over this beast H divan in SH of X. Or if you want to be more precise, maybe I should say, so this X has a structural map to spec K, and strictly speaking, this is module over F upper star of that. Yeah, so this follows from this follows from how these tensor products are computed. Yeah? So this would be SH of X tensor SH. Okay, with modules over this H divan in SH. Okay, yeah, so this is what you get. So you pull back basically this ring spectrum from your base field to X and modules over it. Okay, so that's it. That's what it is. So, what is the corollary about? So this is of course a 600 formalism. Okay, that is for free now. I mean, given all the work. But what is it concretely? So such that here now is the actual piece of information. So this D divan of spec K so this new 600 formalism applied to the graph field simplified drastically. This is just equivalent to mod K derived in your K vector spaces. So on the base field, we just have sort of quote unquote Motivic divanified sheaves on spec K are just K vector spaces. Okay. And the other thing is the mapping spectrum in this D divan, which is this guy here, of some X from the monodal unit in there to the monodal unit there, again, is just omega X over K. So in other words, whatever this beast is, it is such that the endomorphisms of the monodal unit are the divan complex. And so therefore it carries this name with pride. Yeah. So why is that? Yeah, do I want to say something about this or not? Is the question. I think I will skip the explanation of this one here. So part 2 is relatively straightforward. I mean, it's pretty straightforward. You really just unwind all the definitions and you ultimately use that maps into this rho divan right adjoint, which is what basically comes up here, is maps from H divan tensor blah 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 to your thing. Yeah? And then this basically gives you this. Yeah? So in the notes you find a group. It's really just unwinding the definitions in some sense. So let's say 2 is more or less by definition, but plus a little bit of writing. Nothing serious anymore. And I want to comment more on part 1. So why is it that this category here simplifies so much again? So it's a little bit in the spirit of the rigidity theorem, right? There it was also the statement saying that some 6 conformism simplifies drastically. Here, however, it's only proof of the space field. So why is that? So let's so this detail spec K. Once again, if I look here, this is just going to be, so if X is equal to spec K, then this, you can forget about that. You just have modules over H to the in this SH of K. And this goes to mod K. And so what is that functor that we are claiming is an equivalence? Well, this is the functor which starts out life here. So it goes from here to there. This is this bolded on. This has a right adjoint, as we said, and the right adjoint sends the monodal unit to this object. And so therefore you get this functor here, and that's the left adjoint of this. So in some sense, it's the you have that functor and you factor it as a free module functor and then such a functor. Okay. Okay, so this is the functor that we talk about. And so I claim that's an equivalence. And so it's two things. Thing number one is it's fully faithful. So this is fully faithful. So why is that the case? So we have to look at a bunch of generators here, and the thing is, this category SH of K is generated by a very nice set of objects, namely by the motives of X with N, where the X over K is smooth and projective. Yeah, so this follows from the CH descent that we discussed earlier, and again, resolution of singularities. So these objects generate this category. And these objects are noteworthy because they are all dualizable. Okay, so they are dualizable and they are also compact. So the dualizability comes out of this idea duality that we talked about, or Poincare duality. And this compactness, so this I didn't yet talk about so much, but this category SH with this negative topology is actually compactly generated, which follows from the finitariness of excision. Anyway, this is a compactly generated category. It's compactly generated by dualizables. And so if you have a left adjoint, like this one, that has these properties, to check the full faithfulness, it's enough to check it on the monodal unit itself. Yeah, so this is fully faithful, if and only if fully faithful on the monodal unit. Yeah, because so you check it out, you have to check maps out of compact generated into anything, but that compact generator will be dualizable, so you can put it on the other side, and then you play around with the other and the variables. So yeah, so ultimately you boil down yourself to the case of checking on the monodal unit, and that is exactly what's here. So if X equal to K, then we have just omega K over K, which is K. Yeah. So this functor is indeed fully faithful, which uses something non-trivial, but anyway, it's true. And it's also essentially surjective because clearly the ground field maps to K. Now, once again, by what I just said. Yeah, so therefore, it can make equivalence. So that's the argument. Yeah, so upshot is for the dynamic homology, we have the new 600 formalism, which came about by tensoring SH, tensoring it up to basically these modules over the ring spectrum. And it has the property that on the ground field you get something very manageable, and in general it's whatever it is, but it does compute for you what you want. And so in that sense, it's a useful thing. Yeah? And so this has been applied, like I said, to other ring spectra. For example, Swan Chubak applied this to something finer than just an unhomology spectrum that ultimately gives rise to these mixed hot modules of cycle and so on. Yeah? So it's really a very useful and flexible way of constructing new 6-point formalisms. Okay. Good. So that's my second example of a ring spectrum. Now I want to briefly talk about Motivic homology, which is another example. This one will not come about by this paradigm, but rather as my print it up here. So this is Motivic homology. So what is the very quick and pain-free way of addressing or of defining, let's say, motivic homology spectrum? It's the following. To define it, I need to present a filtration of the SH. So we say SH as effective is defined to be the full subcategory of SH is the full stable presentable subcategory. And which one? Well, the generators generated by the motives of X, where X is such a smooth, or in this pro case, we might also watch this weakly smooth Fy and C words. Yeah. So in other words, we have these generators, right? So those were the ones coming from motivic spaces. And this SH was built by these generators, but there we inverted the tape twist artificially somehow, and we don't do this here. I mean, we don't do it in the sense that we never allow ourselves to tensor the new inverse of that tape twist that was visualized here. Yeah, so that's what it's saying. Okay. All right. So quick remark is this SH. Sorry, and yeah, that's one thing, and then SH effective of S twist N. So this is similarly generated by motives of X, and then take twist N where N is larger, greater than 1 to N. Okay, so we twist at least N times. Okay, so this would be the given N is 0. Because you see, this twist is, you know, the twist by positive 1 by plus 1, that's basically direct factor of tensoring with Gn, which is 100%. Yeah, so, yeah. All right, so this is some subcategory, and so the remark is the following. So this SH effective is a monodal, or let's say twist standstill. So this is a non-unital tensor subcategory. So non-unital, because if you take such a thing here and tensor it with another such thing, then you get n of x times x prime, and the twists add up. So this is true for things easier grow. And it's why is it non-unital? Well, because if the n here is strictly positive, then you might not have the little unit there, but of course it is unital for, I mean, this SH effective is unital. Yeah? So this is a really monodal presentable subcategory, and the other ones are almost monodal except for this problem with the unit. Okay, so why do I mention all that? I mention these things because they give rise to the so-called flat filtration. So what is that? So the inclusion SH effective inside SH. So this is by definition a colony preserving functor, right? This has a right adjoint. So which I call Fn. So Fn goes here. It takes SH effective n. So it takes any not necessarily effective thing and kind of chops it up to be some effective, more or less effective, and then there is Fn plus 1 mapping to Fn. Yeah, so here you make it even more effective than here, and there's natural map, and then the co-fiber is called Sn. Okay, so this is the so-called N sites. So good. And so in particular, we have SH effective. If we are already effective, then we can make it sort of a bit more effective by doing this F1, and this S0 will then measure the difference. Yeah, so we have this S0, which will produce for us another effective object. So this is some other, okay, it's hard to say what it is, but we can see somehow for formal reasons. Think of this, I mean, this F1, this F0 and this SH effective is the identity, yeah. So in some sense, it's like you have certain, so this, think of the identity here, and here this is the F1. And so in some sense, we are saying your role object modulo some quote unquote sub object, and well, of course, it's not a sub object, but at the very least, it is true that this S0 here is still like symmetric monoid. So this S0 is like symmetric on that effective category. So think a little bit of you take I mapping to R and this is sent to R not I. This is kind of the paradigm that's work here. Yeah. So roughly speaking. Anyway, so this is a tensor function, a Lex tensor function, and therefore we can apply this to the monodic unit, and we can say this is for the moment just an undeserved notation, but we can say HZ, we define HZ to be S0 of the monodic unit. Okay, so that's whatever it is at the very least a commuted algebra object in SH of S, or even SH if you wish. Which, in other words, is a ring. Okay, and so now, of course, this why do I call this HZ is completely out of the blue, so it comes from topology, where this entire story originates, namely when you look at spectra and more and more suspended spectra, then all of what I said still applies, and there one shows that indeed, if you do this, then you in fact do get the iron spectrum for Z. Yeah? So in that context, it's a fact. Over here, it's now a definition, but this definition is useful because the following theorem, which is very non-trivial, I mean, much more non-trivial than pretty much anything I said so far, I think. So if you want to read up, this is due to the beam, and yeah, also discuss the paper of Perrois and so on. So a nice entry point to literature is this paper by Bachmann on more during spectra, where they discuss this and much more in kind of nice. But anyway, what is the theorem? Theorem is, if we do this, we look up this crazy object and we look now at modules over HZ over this abstract thing there in SH of X. This, and now in there, again, we have another unit, and again another unit, and we twist by one. Then this is going to be our gamma of XZ twist N, where this here is a notation. This is blocks complex computing topics. Yeah. So the cohomologies of that complex are by definition block style Tor groups. And so maybe in particular the form in that category, well again the limit to one twist head shift to n. This is the Tor group, the n Tor group of S. And here X has to be smooth. So Tor groups, as I discussed them in the very first lecture, turn out to be representable by this HC. Okay? And so in other words, all the glory about the homology is also contained in this SH by means of that particular slice, that filtration. Yeah? So I think that's a nice quick way. Of course, I'm not pretending I mean, this is really hard work because where does the hard work lie? The hard work lies in basically, defining this is easy, yeah, but already saying, if you believe in this statement, in particular, you believe in statements like these Char groups, they have intersection products and all this, which is actually, I mean, the Char groups and the higher Char groups, and that is actually already a pretty delicate thing, yeah. So this tells you it can't be that easy because it gives you non-trivial things on the level of these Char groups. But yeah,
Sorry. This HC is this one that you define, say, at the start of the lecture. So you have one map from spectra to SH, and you.
No. Yeah, that's a very good question. It is not. It's really not. No, it's not. It's not quite. Yeah. So yeah, thanks that's a good catch. So if I do this HC in this sense from earlier, I just basically tensor up the original coefficients from spectra to Z modules, which is not going to be necessarily oriented, whereas this one is. Yeah, good question. So I shouldn't use. Yeah, okay. This notation is also set in stone somehow, but it's a different one. With Q coefficients, these things agree often, but also not always. So there is the so-called plus and minus part in the SH, and so modules over HQ in the sense from the beginning of lecture splits into the so-called plus and the minus part. This minus part is the non-orientable one, and the plus part that is this one. Yeah, so they are related, but it's not quite identical. Yeah. So yeah, thanks for asking. All right. So what's the time? Does someone have the time? Okay, I have half an hour left. Okay, good. Yeah. Last thing I want to talk about is game theory, which again admits kind of a nice high level approach to constructing this in terms of a ring spectrum. I will try and say a few words about that. So first of all, yeah, it is representable. And how? So here's a proposition, which is due to model velocity. I believe this statement was certainly the main motivation for them to develop this theory in the first place. So the statement is the following. So if S is the regular scheme, and X over S is smooth, then we have this category of Motivic spaces, and here we want to take point of Motivic spaces and take them as knowledge topology. So now these topologies start mattering. So this is what we have. Sorry, we already because the mapping space is what I want to look at inside this formula things over S. And again, this has a monoidal unit. Yeah, it has a monoidal unit. I want to look at that lower chart of monoidal unit and then plus to make it point object here. I think that's not so relevant. But anyway, so that's what I'm writing down here. And then I have this L mode, this motivic localization of what Z times the infinite dimensional gross money. That is not the same as the F9 gross money, but rather, and this is K of X. So let me say what all these terms are. So what is this GER here? So the GER is the co-limit over two variables, namely you take GER D and let's say, yeah, R or something like this, yeah, maybe R. Anyway, so we take n-dimensional, let's say locally free sheaves operating n inside O D plus n, and then we let n and d grow one by one and take the co-limit of this. Yeah, so this is still an in scheme but it doesn't really matter. It doesn't matter that it's a free sheaf. So we have that, and we can take z many copies of it and apply this L mode to that. Okay, that's some object. And what Motivic showed is that this spits out algebraic K-theory. So the proof of this is, I mean, it's not a one-liner, but it's not excessively difficult. So that what one shows is that this here is related to this VGL thing, yeah, and then it relates to the state here. So this is, I mean, I want to take it as a black box. I just want to say there is a certain very canonical geometric object, namely basically this Grassmanni, which gives rise to K-theory by means of mapping into it, basically. Yeah, so good. That's convincing. However, what is not so obvious is how to make this. You see, on K-theory we have the multiplication, we have tensor products. We want this to be a ring spectrum, as opposed to just a collection of homotopy groups. And so the question is, what model do you find that captures that structure? And this, and that's the question number one. And the question number two is also how to adjust this up into a spectrum as opposed to some Motivic space. So both of these things have been sort of addressed. So there is a way, maybe, let's say, theorem to lead you to U. There exists spectrum which will denote KGL. So this is a limited algebra object in SH of again space Z. So what we were looking for, such that the levels of this KGL are just Z times the Grassmanni, right? Well, such a spectrum is a collection of Motivic spaces, and they all are the same, and there is certain depth between certain bonding between them, so which I would not want to discuss. And so you proved that you can, if you are clever enough, then you are able to sort of find the multiplicative structure on some ring spectrum that gives you back the original one. So that is good, but what I want to do is a slightly different approach. I want to at least sketch how this K comes out of non-geometric force. And I think that's a nice approach as well. So I will not say more about this theorem, but rather I now want to present to you a way of constructing this KGL in these terms. Yeah? So the goal is now the following. So we have this SH of space Z. We are trying to come up with this over one commutative motives, SH non-commutative, still over space Z, and a functor, which I call rho non-commutative. So this is very similar to what was the Vodelan a while ago. So this again is supposed to be a lexicommetric monodal colony preserving functor, this rho and C, with the property that in here you have the monodal unit, and that is actually, it will turn out the so-called homotopy K-theory study. Yeah? So the homotopy refers to the need of rendering this homotopy invariant, which was not apparent here because here S and therefore also X were regular. Right? So in that case, K-theory is homotopy invariant in general, but up to that small point, the monodal unit in this category that I will discuss will be the K-theory, and therefore we can send this back here using rho commutative right adjoint, and this we can then call KGL. Right? And then we'll have, by the setup, this will have all the structures we want. Yeah? So this will be not just a random object, but rather a commutative algebra object in the stage. Okay. And module over that will be these so-called K modules that, for example, Jens Eberhard has studied a lot of his work and so on. Yeah, so this is kind of a rather more sister of this Motivic homology spectrum. Maybe just as an aside, I'm not going to do it today, but if you do it with KGL and tensor this with Q, then you're going to get this HQ, well, in that Motivic homology sense, with shift 2. Yeah, so this is kind of a high level way of of seeing the comparison between K groups and char groups and so on. Yeah? But anyway, I will not go into this too much, but at least I want to give you an idea what the SHNC there is and how we can navigate between these two sides. Okay, so what are these non-commutative models? Since time is short, 20 minutes is not a lot for this. I'm trying to, I don't want to spend too much time on that because it's a little bit outside the scope of what I'm trying to do. But so maybe how do I approach it? I think I will start writing down the definition and then spend a little bit of time on saying what these things are and try to wave my hands. Okay, so definition of, and by the way, all what I'm saying here now is due to the work of Jakob who did that. So what is this X fish? So for simplicity, let's say X is spec A. So it's not completely necessary, but I want to sort of focus on the essentials here. So SHNC of X is defined in a way which is kind of similar to the definition of SH. What was the definition of SH? We started out with smooth scheme over our weights, then took pre-sheaves, then localized at A1 in the stage topology, and then we rendered the taped thing in verb. Okay. So here it's similar. So it's pre-sheaves on something else, namely smooth non-commutative schemes over X, and I will say what this is in a moment. And for technical reasons, I prefer working with spectra right away as opposed to anima, but that's not a big deal. And then a certain, let's say, a W miss and A1 localized, and that's it. So you see there is a difference between, an apparent difference between that definition and SH, because in SH we used to still do this tape twist. We ran the invertible. That turns out it's not necessary. But anyway, let's for the moment accept this as a definition. So what is this SM and C? So SM, X, and C is the following. Here's the definition. So modules. So first of all, we have mod A, which is the derived category of A modules, A of our brother. And that is an object in PRL. So we can look at A linear categories, right? That's what this is. A linear presentable categories. This is, however, more. This is not only a random category, but it's actually a compactly generated category, right, by the perfect complex. So that's how actually an object. Okay? So mod A is the int of perf A. So we can look at compactly generated categories that are A-linear. And that is also, it's a bit of a mind twister, but this is a compactly generated category, and we take the compact object from that. So, yeah, this looks like, I don't know, it looks crazy. But that's the definition. And another definition, which is maybe a little bit more your taste, is SM projective, SM proper. That's what are non-commutative proper schemes. These are similar. Mod A, PRL omega, and then in there the dualizable objects. Okay, so now I have to say a few words about this because otherwise it's, I think, completely intangible. So first of all, what is something that one should say here? So this PRL omega is itself compactly generated. Okay, maybe by what? By spectra, which is also the monodic unit. Yeah, so this is a non-stable category which is generated by only one object, namely spectra, and that is compact. And that same fact persists if you look on mod A. So this guy here will be generated by its monoidal unit, which is 1K. Okay. So in other words, these compact objects are basically coming up all of this one generator under finite tolerance and grid traps. And dualizable objects are, well, they are whatever they are dualizable. It turns out that, like I said, the monoidal unit is compact, and therefore any dualizable object is compact. So we have such an truth. So smooth proper schemes in that non-commutative sense are smooth in that second non-commutative sense. So and in fact, one or two facts is so why do these why does this abstract nonsense reserve its name smooth and smooth proper? So facts. So if you have spec B over spec A, then you can look at mod B. So this is the representative category, which is A linear. So this is an object in mod A PR omega. Okay. And now the claim is, so I mean this is for free, and now the claim is spec B is, or let's say, yeah, mod B maybe. So this guy here is compact, which is what I declared smooth non-commutative to mean, exactly if B is smooth and of finite type. Okay, so this is a statement due to, I believe it goes back to N basically, but it's also in the thesis of a while. Yeah, so this new thing there deserves to be called smooth because for the categories that come from sort of regular algebraic geometry, you recover that. That's fact number one. And fact number two is what about this smooth proper there? So if you have x over spec A, well, I think I should say over spec K over field, then Q co x, that is again an object is a K-linear category, it's in mod K, omega, okay. And now again a similar statement, so x is smooth and proper in the usual sense over K, different only if x rises there. So if mod x, sorry, if Q co x is dualizable. Yeah, so in other words, these non-commutative variables there, they do recover at least what we are used to originally, but of course they give you much more freedom, yeah, because you have many categories that are linear but might not be of mod something, mod of a commutative ring. Okay, so I always give you some feeling that this is not a complete nonsense here, these definitions. And now so my goal, so that gives you some idea about this. Yeah, so think of this as being a replacement for smooth schemes that is larger in the sense that you have, you just have more objects basically. Yeah? So this could be, I mean, categories over a non-commutative ring will also, I mean, not for every ring of course, but it can also be. Yeah? That's kind of the extra flexibility that you gain here. Okay, good. So now, this replaces smooth schemes. Now I have to say something about this NIST. So how can you sort of, I mean, this image is maybe a little bit of an overkill here in terms of material, but we want to impose a certain locality condition that resembles something like this NIST topology. And if you think back to this NIST topology was characterized by these distinguished squares, right? We had these NIST squares where basically you have some v over x and some u. So this was open, and here f inverse of u, and we had the z here, which was complement, and the inverse of z. And this was supposed to be an isomorphism, right? This was the defining nature of the initial topology. And so where the f was eta and this was infinity. So the condition that is étale will not really resurface in this non-commuted context, but the condition of basically saying, okay, I want to cover my x by u and v in such a way that this complement here is that is something that one can follow. So here's the definition. So a non-commutative knowledge square is a complete diagram. So let's say I fix just for simplicity at my F-line base scheme. So in the notes you find this for schemes, but let's not worry about this. So modules in mod A. So modules once again A presentable compact general. It's a complete diagram of the following form. So I'm writing it down like this. So ZB U U. So so this is meant to be a replacement for this one here. So now I have to impose conditions. And these conditions are the following such that, so remember, these are now categories, right? All these four things are categories. You want to think these categories are Q-code on a certain scheme. That's what you want to have in mind. If you want to somehow impose conditions on these categories that, if these categories were a Q-code scheme, give you back sort of conditions like these. So that's the third. And now the incrementing this third is the following. So such that this is a pullback and a push out there, right? So in this PRL omega, you have more about pull and push out. So we want this to be like that. Of course, that resembles the condition that this is a pullback here and that this is that the x is kind of covered by u and v. So that covers kind of in some sense this. And so what about that part here? So the pull square and the horizontal functors are strongly continuous localizations. Strongly continuous localizations. Yeah, so what does that mean? So localization means your functor has a fully faithful left adjoint. And strongly continuous means right adjoints, I meant to say. And strongly continuous means these right adjoints have to be fully preserving as well. Yeah, so in the notes I've written down more about this. Yeah, so this is meant to be, so this localization is meant to be the replacement for this being an open embedding. Yeah. So the thing is, if you have such a thing, then you have Q-co X, that goes to DJ, the alpha star, Q-co U. So we have this kind of an injunction here, and this is fully faithful and preserves columns. Yeah, so that's the situation here. And so we're kind of implementing that situation. So whatever it is, it's a certain definition that makes sense on a purely categorical level. Yeah? And so then what does it, this knowledge square, we define this as knowledge excision in some way, and there's a very similar, practically identical way of implementing that. Yeah? So maybe I will, in the interest of time, just say this. So there is a way of talking about this knowledge topology in this non-commuted setting. And of course, A1, there's no problem about that. You can impose A1 invariance, and that's what it. Okay. And one slightly surprising thing is the remark. So why is there no inversion of the Tate sphere here in some sense? The reason is the following. So if we say if we define the non-commutative mode of some x to be just this Q-co of x, which is going to be an object there, then we can say the following. So you map from the motive of some spec K, let's say, non-commutative motive to the motive of P1. So what is that? So now here we talk about fast-growing sheaves on P1, and here we talk about sheaves on point. But so we not nothing but P colon P1. And the fact is this category is generated by O and O twist 1. Okay, so as a category. And so this Motivic topology has the effect of under this non-commutative Motivic thing, it has the effect of saying this is basically Q-co of point plus Q-co of point. And so because of this so-called semi-orthogonal decomposition. Whatever it is, it turns out the non-commutative model of P1 is already point plus point. It turns out, and so therefore, if you do this cofiber of one point to all of them, it is already invertible. Yeah, so the cofiber of this is invertible already, and so that's why it doesn't talk. Yeah. Okay. Anyhow, that's what is, and so now we can say, instead of time, we can say what is. There is a pointer from the neutral SH to that SH, non-commutative. So, composition. Again, all this is neutral variable. So there is a tensor and model and polynomial, I mean continuous pointer as follows. So SH of X maps to SH non-commutative of X. And how is it sort of pinned down? Well, you have smooth affine schemes over X, right? I remind you once again, this is basically built out of those. So we have a certain functor, and functors out of here into somewhere else, you are characterized in terms of those. And so what do I do? Well, I go from here to this smooth non-commutative over X. And this just sends such as TMC to Q-co of T. Yeah? And by what I said in the beginning, if this T is smooth, this Q-co will be smooth in the non-commutatives. And so the existence of this functor is a little bit not trivial, but okay, it exists. And then here we have canonical functor in the same way. Yeah? So this functor exists basically because of two observations. One is that, once again, this classical smoothness relates to this finiteness condition with this compactness condition here. And then on both sides, we have built kind of set. I mean, here we have this Motivic topology, here we have this non-commutative Motivic topology, and the fact is that if you apply Q-co to a classical Motivic square, you get a Motivic square that makes sense. Okay, and the A1 is been inverted, and then this last thing here, which tells you don't have to tensor invert. That's the result. Okay, Robala constructs such a category, and okay. And now you might wonder, okay, what is this all about? What does this really buy? And that's what I want to get with. And if you wish, you can read all that in the notes. So it's a little bit long to say all that really carefully, but maybe you're interested, maybe not. What is the punchline somehow? The punchline is again you feel wireless. The monodic unit in this stage non-commutative of, let's say, so Z is just this homomorphic you're expecting. So, which is of course a fantastic result, right? Because you do something in terms of, I mean, it's a kind of abstract. On the other hand, you never really said anything about K theory, right? I mean, this was just really, see, this, I mean, makes some good sense. Right? So it's just sort of you play with the linear categories, insist on this being compact, and then you invert a certain amount of localization in some sense, and this A1 would not be necessary for that, then you would just get K theory, and it comes out. Okay, so very, very cool thing. So this statement relates also, I mean, as I said here, it's with the while, like I said, it also relates to the work of Lundberg, Gertner, Wada, and other people who have expressed the universal property of K theory in as the universal localizing invariant. So again, the notes you will find more about this. So maybe the only thing I want to say is how this even makes sense, how this proposition makes sense, or how can I even say that KH is a monoidal unit here? Yeah, so how is it even an object? That's what I want to end with. So remark. So how is this KH an object here? This first of all an object in this SH non-commutative. So let's parse the division again. So we look here. It's supposed to be a pre-sheaf of spectra having all these, I mean, like this. Yeah? So maybe I'll just say or can so or is not a good idea. So it's okay, theory is a part of the point that takes any compactly generated category and assigns it to a spectrum. Yeah, so here theory goes from DRL omega spectra. Yeah, so you part to compact equations and then you do the theory spectrum. Okay, whatever it is, that's something, and and now basically we are changing all these things there. So we have this Sm non-commutative over your base. We define this to be the compact objects in here. So it's mod Q cox omega, and these are precisely the compact objects. So we forget about that. And then we also forget about the linearity. And then we define this thing. Yeah. So this is, I mean, this is just such a functor, and K theory, once again, it has the property of sending these, we talked about this push out of Kubek squares, and it will have the property of sending such push out of Kubek squares to hyper sequences. That's the sort of localizing feature of it. And then that is this A1 invariant that was kind of sort of made by this up. So that's, I mean, what I'm trying to say here is that this category defined like so is really the natural home for functions like K theory spectrum functor, and especially in this context here, the homotopy K theory. And it turns out that it has this very strong universal property. The monodal unit in here is that K theory spectrum, and then therefore we can say, I mean, sort of after all this has been done, one can say define KGL to the row non-commutative right adjoint of this monodal unit, which is sort of the K theory spectrum. And that will be that's the end of my lesson today. So what I was trying to do here is to give you a little bit of a toolbox of how can you cook up new ring spectra from old ones or from other theories. So basically you have to come up with functors out of SH to something else, which have to be reasonably monoidal, and then often the right adjoints to these functors turn out to be interesting ring spectra, and modules over those will be then more or less computable depending on what the spectrum is. Okay. That's all.